Hey everyone, Mr. Fransky here. Today we're going to be talking about finding the area between two curves. So we've talked a lot about finding the area between a curve and an axis. Haven't talked a ton about finding the area between two curves, so that's what we're going to focus on today. So we're going to start with some bell work with some stuff that we talked about in 7.1. First of all, we have a calculator OK problem where we're given a rate. Remember, this is one of those we're given a rate. We're looking for it to go down to the amount. So the rate at which grain is loaded on the train is modeled by R of t equals 2e to the 0.5t. At t equals 7, 6,000 pounds are on the train. How much is there at t equals 10? How about at t equals 0? So one going forwards, one going backwards, pretty standard. Then b is we're given a velocity graph. So this is v of t, and this is t. And we're asked when the particle's moving forward, backward, what is the total distance traveled? Remember, distance traveled, that's a kind of a key term for given these graphs. From 2 to 5. And then if v of 2 is 4, find the initial at 0 and the final position at 6. So if you want to try these on your own, you can, and then we'll try them together. Alright, so this problem, remember we have our special tower of functions. You have the rate, you have the acceleration, so r prime t up here, and then you have the amount. Really the first two are the ones that you're going to focus on, right? R prime is like the rate that the rate is increasing. A down here is the amount. R right here is the rate, which is what we're given. So to get from the rate down to the amount, we can integrate. And remember, we can always choose what value we want to start integrating at. And usually we want to start at a value that we know. So in this case, because we tell us at 7 it's 6,000 pounds, I'm going to integrate from 7 to t of r of t dt. And then if I'm starting at 7, when I plug 7 in here, I should get 6,000. So I'm going to add 6,000 to it. The other way to think about this is that if you integrate from 7 to t of r of t dt, the antiderivative for the rate is the amount. So that should be the amount at time t minus the amount at time 7. So that's why I chose 7, because I know the amount at 7. If you add the amount at 7 to both sides, which is 6,000, then you have the equation we have right here, right? 6,000 plus the integral from 7 to t of r of t dt is what's going to work out for us here. Okay? So this is kind of in parentheses. Usually we jump straight to here. So what we want to know now is how much is there at t equals 10. So amount at 10, dot t, 10. So the amount at time 10 is going to be 6,000 plus the integral from 7 to 10 of r of t dt, which is 2e to the 0.5t. Now this is a calculator question. Don't waste your time finding an antiderivative for this. We can find an antiderivative for this. It's pretty easy. But if we're given a calculator, we might as well just use the calculator. So let's hop over to our calculator. Let me keep them. Alright, here we go. Okay, so what did I have? It was 6,000 plus the integral. So go to menu, calculus, integral. There we go. Integrating from 7 to 10. What was it? 2e. In order to get the e, we have to go right here next to the 10 to the x. So 2e to the 0.5t dt. Enter center. That's it. 6461. How many decimal places do we need? I think we need at least 3, so I always go to 4. So 6461, 0.1908. So 6461 point, what did I say, 1908? 1908. And this is in, what, pounds? Yeah. And that was the amount at 10. It makes sense. It should be bigger, right? E to the x is always increasing, so that should be a bigger value. Alright, and then how much is there at 0? So the amount at 0, I'll change back to black after I get to the next slide here, 6,000. Plus the integral from 7 to 0. Trust the math here, right? We're integrating backwards here. That's fine, though, because we're going back to see how much there was at 0. So of 2e to the 0.5t dt. So you could change this to a subtraction from 0 to 7, but I'm just going to leave it alone because the calculator will take care of that for me. So I'm going to do 6,000. I'm going to check you're going to hit up twice here. All I'm going to do is change that 10 to a 0. Should be less than 6,000. Looks like they started with 5871.5381. 5871.5381 pounds. Okay. These are easy problems. Don't give away the easy points. Huh? Alright, let's see what we got with that velocity problem. Okay, so in this problem, we've got a particle that's somehow maybe traveling on a line, and we're asked first when the particle is moving forward. So this is our velocity. with respect to time. And so we're going to be moving forward whenever velocity is positive. So that happens whenever this graph is positive above the x-axis. So that happens 0 to 2, and also from 4 to 6. Okay. When is it moving backwards? Just when it's below, so 2 to 4. Distance traveled from 2 to 5. So here's 2, here's 5. That is not just an integral, right? I have to add up the pieces that are positive. I'm going to look for a positive area here and positive area here. I'm going to add them together. So that is going to be the integral from 2 to 4 of v of t dt plus the integral from 4 to 5 v of t dt. And we're going to make sure these are positive numbers, so that we're going to take the absolute value of each one. So 2 to 4, looks like we have two triangles there that each have an area of 1 by 1 divided by 2, so these are each 1/2. So this is going to be negative 1/2, negative 1/2, so that's a positive 1 altogether if I take the absolute value. Add to that the integral from 4 to 5, 1 by 1/2 divided by 2 is 1/4. That's it, I guess. Huh? That's total distance traveled, and in this case, I don't know, didn't ask for units, so I'm not going to worry about it. Now they tell us that v of 2 is 4. Okay. So at 2, I know that it's moved 4 units, right? Or it's at positive 4 units. So the question is, find the initial and final position. So what I have to do here is set up a tower of functions. So v of t, we have a of t, and we have x of t, that position. So then we know that v of 2 is 4. So the position is going to be 4 plus the integral, from 2 to t of v of t dt. Just like with our rate function before, we had the grain, we know we're starting at 4, and that's when I'm at 2. So if I integrate forwards, it'll be going from 4. If I go backwards, it's going back from 4. Okay, so they want to know the initial and final position. So x of 0 is going to be 4 plus the integral from 2 to 0 of v of t dt. That is 4 plus, so integral from 2 to 0, I'm going to write that as minus integral from 0 to 2. Because we're going backwards, so it makes sense. We've been increasing up to this point because we had positive velocity. So we're gonna, when we're going back to 0, we're gonna take something away. So v of t dt, that's a semicircle. It's half of pi r squared, which is just pi because r is 1. So this is 4 minus pi over 2. There we go. And I also asked for the final position. So final position, x of 6. Is going to be 4 plus the integral from 2 to 6 of v of t dt. Now this time, the negative area is going to count as negative, because that means we're going backwards, and then the positive will cancel some of that out. I don't know if it'll cancel all of it out, but it'll be close. So that's 4, and it's going to be minus this guy down here. We already found that, it's 1. And then plus, let's see, 1/2 base times height, 1/2 times 2 is 1, times 1 is 1. Oh, they cancel out, so it's 4. Okay, so 4 minus pi over 2 at the beginning, then it increases up to 4, then it decreases a little bit, then it increases, and these two areas are exactly the same, so it just gets it all back. Cool. All right, so let's jump into some area. So, any idea how we can find the area between the graphs? So looking for the green shaded area here and the green shaded area here. If you want to pause the video and give it a shot, you're welcome to do so. All right, so for the first one, I think you could do this using geometry, right? You could find the area of the big triangle, right, for the red graph, f of x. You could subtract the area of the smaller triangle here. That wouldn't be too bad to do. This one, we can't really do that, right? But I think we can use integrals. So if you think about, and this one actually works too. If you think about the area of this triangle down here, what is that as an integral? Well, that is the integral from 0 to 3 of g of x dx, right? That's the area of this triangle right here, and I'm taking that away from the area underneath the red graph, all the way down to the axis. So that would be the integral from 0 to 3 of f of x dx. Over here, we should be able to do the same thing. If we drop some lines here, the area underneath f of x is the area from the blue graph all the way down to the axis. So that would be the integral from 1 to 5, it looks like, of f of x dx. But I don't want all of that. I only want the area that's green shaded. So I have to take away what? All the area under g. So that is minus the integral from 1 to 5 g of x dx. Now let's look at these and see if we can remember something from our integral properties that will make this a little easier. If I'm subtracting two integrals with the same limits, can I just do that as one integral? I think I can. This would be 1 to 5 f of x minus g of x, all dx. I think you can do the same thing over here, right? This would be integral from 0 to 3 of f of x minus g of x dx. So for both of these, it looks like we took the top function, we subtract the bottom, and then we integrate from the beginning to where we want to end on the x-axis. Okay? It doesn't seem too hard. So this is the general idea for area between curves. If you have two curves, okay, f and g, f of x, g of x, and you want to find the area, remember everything we did with area came down to rectangles. So let's see if we can get that idea here. So if you were to do rectangles here, doesn't really matter if you use right side, left side, midpoint, but it looks like I'm doing midpoint rectangles here. Okay, so if you were to have a bunch of rectangles here, remember the more rectangles the better. So the more rectangles you have, the more accurate your area is going to be. But if I find the area of these rectangles, let's think about what it's going to be. The width is going to be determined by the number of rectangles I use, right? So let's call the width delta x. The height, though, to think about the height of a rectangle, I think we can use some magical technology here with colors. If you think about this blue line right here, that length of that blue line at x is f of x, right? The height of that blue line is f of x. That's all the way down to the axis. But that's not the height of the rectangle I want. I only want the height between the two curves. So what do I have to take away from that to be able to find just the height that I want? So I'm actually looking for, let's make it red. So I'm actually looking for, get the red one. So I'm looking for this distance right here, right? So if I take the blue, what I want to take away, is, let's use green, is this little green guy down here. What's the green part? The green part is g of x. So to get the red part there, I think what I have to do is actually just subtract, the red again. So what I have to do to get the red is just subtract g of x from f of x. So it's f of x minus g of x. Right? Because it's the blue line, take away the little green line, we'll leave you with the red line. So the height of each one of these rectangles is f of x minus g of x. So really all we're doing here is integrating from wherever we want to start. Let's call it A. I'm running into my pause button here. Let's just use that color. Okay, so to find the area between the curves, let's say we're going from A to B. We're going to integrate from A to B of f of x minus g of x dx. So all this is the top function minus the bottom function. If you do it the other way around, you'll get negative values, which you don't want. Okay, so you do top minus bottom. That's it. That's really the general idea for finding the area between two curves. Now, people always ask me, first of all, what if they cross? Something like this. Okay, let's say you want to find the area from here to here between the two curves. Okay, so you're going to find this area. Well, if you're doing top minus bottom, let's say this is f of x and this is g of x, what you would have to do is you have to find the intersection point here. Let's call it C. So what you do is you integrate from A to C, f minus g dx, and then you would add to that the integral from C to B of g of x minus f of x dx. Okay, so not too bad. You got to find the intersection point, then you integrate. If you don't do that, you're going to have the same issue as when we do with total area, right? This is always a total area question. You're going to have a problem with getting negative values. So you want to make sure that you always are doing top minus bottom. It's always going to need to sketch a graph if you can. If you have a calculator, graph it on your calculator. Do something so you can see which function's on top and which one's on the bottom. And then integrate, make sure that you're doing top minus bottom function. So the other question I always get is, what if one of the curves is negative? They say, does it still work if the curves are negative? It does. So let's say that you have a function like this and a function like this. Okay? So to find the area of one of those rectangles, you still want to know the distance between them, right? So if we go back to our magic colors, use a different color this time. Let's say you want to know the length of, let's use yellow, the length of this yellow line. Okay, so if you take the length of f of x, let's call it purple here, f of x, so that's f of x right there, right? F of x distance from the x-axis up to here. And then you think about g of x, let's use this weird color, g of x is down here, right? So this guy right here is g of x. So g of x is a negative value. Let's think though, if you do f of x minus g of x is a negative value. Let's say it's like negative 3 there. And let's say f of x is like 2. I use purple. Right? So if I do 2 minus negative 3, what does that give me? It gives me 5, right? Because you're adding it. That's the entire height. So it always works. Okay? You don't ever have to think about this again. Just know that top minus bottom always works. Always. It always works. So just trust it. This is what kind of like with the integration that we were doing yesterday in 7.1. Just trust that the tower function works. Trust that you're allowed to integrate from a starting point. Don't worry about doing fundamental theorem every time. Just trust that the math is going to work. Okay. So if they're both negative, same deal, right? If you take f, which is going to be a negative, let's say it's like -1, and then you take g, let's say it's like -3. If you do -1 minus -3, it's going to give you 2, okay, which is the distance that you want right there. It's 2. Okay, so it always works. Don't worry about it. All right. So bottom line, integral from a to b, f of x minus g of x dx. Okay, so this is always going to be a top minus bottom function. Fg. Now, sometimes we define curves in terms of other variables. So this is something you're going to see a lot, especially when we get later into chapter 7. Let's say that you have two functions that are defined in terms of y instead of in terms of x. So maybe you have one that looks like this and one that looks like this. Okay, these are functions of y. They're not functions of x, but they pass the horizontal line test. They're functions of y. Let's say this one right here is f of y, and this one right here is g of y. Instead of doing top minus bottom, which one of these, let's say that you're doing a rectangle like right here, which one of these do you think is a bigger y or bigger x value, right? Because x is a function of y. So here you do top minus bottom. Here you're going to do right minus left. Right is going to have a higher x value than left. So you do integral. In this case, you would do, if you wanted this area in between here, you would do g minus f. G of y minus f of y. Okay, from, I guess, let's call this a, let's call this b up here, a to b, dy. So in this case, you're always doing right minus left. Right minus left. So let's see some examples where it makes more sense to do things in terms of y than in terms of x. Especially if you're given a function in terms of y, it's definitely the way to go. So speaking of problems, let's try some example. So these are kind of 3 difficulties of questions. I've got mild, medium, and hot. And these are all no calculator problems. So the first one, I give you the graph. The last 2, you kind of have to draw it for yourself. I always think it's a good idea to draw a picture of these. So if you want to try these on your own, you can. Or if you want to follow along with me, you can do that too. But let's jump in and see what we can figure out. So first problem, looking for the area between secant squared, that's this guy up here, secant squared, and sine x, that's this guy down here, from 0 to pi over 4. Okay, so we're doing top minus bottom, so we integrate from 0 to pi over 4. Top function minus bottom function. Secant squared x minus sine x dx. Antiderivative, so we have to do antiderivative of secant squared, that's tangent x. Antiderivative of sine is negative cosine, so it's going to be plus cosine x. And we evaluate that from 0 to pi over 4. Tangent of pi over 4, tangent of pi over 4 is 1. Plus cosine of pi over 4, which is root 2 over 2. And then we subtract off. Tangent of 0 is 0. Cosine of 0 is 1. Okay? So let's see. We have 1 plus root 2 over 2 minus 1. So that is root 2 over 2. Not bad. That area here is root 2 over 2. So nice trig values, nothing too tough. Nice and mild. And that's why I'm medium. Area enclosed by, so enclosed means the area that is cut off, so by the 2 graphs. So 2 minus x squared and negative x. So 2 minus x squared, this has been moved up 2, and it's flipped over the x-axis. So 2 minus x squared is going to look something like this. There we go. And then negative x. Negative x looks like that. So we want to know what the area is enclosed by. I'm right here. So what do we have to find first? Well, I think we have to find those intersection points, right? So I want 2 minus x squared to be equal to negative x. So I'm going to put everything on the right so that I get a positive x squared there. So I have 0 equal to x squared minus x minus 2. Hopefully that's factorable. Let's see, x and x, minus 2 plus 1. So this guy right here is positive 2. This guy right here is negative 1. So we're integrating from negative 1 to 2. Those are our intersection points. Don't care about the y's because we're doing everything in terms of x. Top function minus bottom function. So we're going to do 2 minus x squared minus negative x. If this function is more complicated, make sure you use parentheses. Very, very important. AP loves to give you things that have like just 2 terms, like negative x plus 1, something like that. You would have to make sure you have that in parentheses. You're subtracting the entire function. This is dx. Alright, so let's rewrite that a little prettier. Negative 1 to 2. I'm going to write that as negative x squared plus x plus 2 dx. So antiderivative, negative x cubed over 3 plus x squared over 2 plus 2x, evaluated from negative 1 to 2. 2 cubed is 8, so I have negative 8/3. Plus 4 over 2 is 2. And then plus 4. Then we subtract off, put in the negative 1. Negative 1 cubed is negative 1. Negative 1 is positive 1/3. Plus x squared over 2, so that's plus 1/2. And minus 2. So be careful with your negatives here. So this is going to be negative 8/3 plus 6 minus 1/3 minus 1/2 and then plus 2. Negative 8/3 minus 1 more third is negative 9/3. That's negative 3. Plus 6 plus 2 is plus 8 minus 1/2. Negative 3 and 8 are 5 minus 1/2. That is 4 1/2. That's fine. We can leave it like that, or that'd be 9/2. There we go. Cool. All right, and now for the hot one. So the area bounded by x plus 2, root x, 0, and 2. Let's see here. Y equals x plus 2. X plus 2 looks something like this. Okay. Root x looks something like that. 0 is right here, and 2 is right here. So we're looking for this area right here. Whew. Okay. So based on the way we've done things before, we need to know this point. We need to know this point. And look, this top function is changing, right? Our top function is x plus 2 for a while. Then it's just y equals 2. Okay, so it changes. So we're going to have to do two separate integrals with this if we do it with respect to x. So what we're going to do here is we're going to integrate from negative 2, right? Because it's negative 2 right here. Negative 2 to 0. Top minus bottom. So that is x plus 2 minus 0, right? That's not too exciting. Dx. Because 0 is the bottom function here. So you could just do integral of x plus 2, right? And then we're going to add to it the integral from 0 to, we have to figure out what this value is right here. From 0, so we know the y value is 2. Something, comma, 2. So you think the square root of what is 2? Well, the square root of 4 is 2. So 0 to 4, top minus bottom function now is going to be 2 minus root x dx. Top minus bottom, always. Okay, so antiderivative, x squared over 2 plus 2x, evaluated from negative 2 to 0. Get lots of practice with evaluating definite integrals here in this unit. And then it'll be plus, let's see, 2x minus x to the 1/2 over 1/2, which is 2, x to the 3/2, excuse me. I gotta think about this. It's x to 1/2, so it's x to the 3/2 over, so it's 2/3 x to the 3/2 from 0 to 4. Okay, plug 0 in here, everything goes away. Wonderful. Plus, so it's going to be 0 minus, plug negative 2 in, that's 4/2, which is 2 minus 4. Then we add to that, let's see, plug 4 in here, you get 8 minus 4 to the 3/2, that's the square root of 4 is 2. 2 cubed is 8 times 2 is 16/3. And then you subtract from that, when you plug in 0, you just get 0. Okay. So 2 minus 4 is negative 2. Negative 2 is a positive 2. And then we add to that 8 minus 16/3. 8 is 24/3. Minus 16/3 is 8/3. 2 is 6/3 plus 8 is 14/3. There we go. Cool. Now, even as I was going through this, you might have thought there's a better way to do this. And I agree, there is. So if you had done this one way, so is there a better way is the question. One would be that you could use geometry, especially for that triangle at the beginning, right? If you just focus on that triangle, this is 2, this is negative 2. So just this triangle right here is just 1/2 base times height. Never forget about geometry. 1/2 times 2 times 2, that should be 2. Okay, let's go back and see, yes, that area of the triangle by the integral also gave us 2. So you could find that and then do the other part to find the 8/3 and then add them together. That's one way you could do it. Another way you could do it is with respect to y. Okay, so we think about this instead. This is 2. So we think about this entire area instead as, instead of y equals x plus 2, if we solve this for x, so x equals y minus 2. Solve this for x as well. X is equal to y squared. So this function is y squared. This function is y minus 2. And then if we integrate from 0 to 2 along the y-axis, so we're going to be integrating dy. So we're using horizontal rectangles now. So if you integrate from 0 to 2, right function minus left function. So it's going to be y squared minus parentheses y minus 2 dy. Let's see if we get the same thing. So this time we have one function, which is kind of nice. So let's rewrite this as integral 0 to 2 y squared minus y plus 2 dy. So this is why it's kind of nice to do with y, because it's just one function. So that's going to be y cubed over 3 minus y squared over 2 plus 2y, evaluated from 0 to 2. Plug 2 in, you get 8/3. Minus 4 over 2 is 2, and then plus 4. And then minus, put 0 in, it's all 0. So let's hope this works. Whew, let's see. So 8/3 minus 6/3 is 2/3. Plus 4 is 12/3. Yeah, 14/3. Check that out. I always love it when it works out like that. Cool. So, a little bit faster. Sometimes changing variables to y's is necessary. In this case, it wasn't necessary. We were able to split it into 2 chunks using x, but sometimes it's definitely easier to use y. So, what if you have a calculator? So here we're asked to find the area enclosed by x cubed minus x squared minus 13x and g of x, which is negative x. So first thing I would probably do with this is graph both parts on my calculator. So let's do that real quick. Here we are. So if I had to graph here, and I'm going to graph x cubed minus x squared plus minus 13x. So x cubed minus x squared minus 13x. Alright, so we got this kind of cubic looking thing. If I can maybe zoom out a little bit. Let's go to zoom out. The center right at the middle. It's probably going to zoom out more than I want, but that's okay. Now let's do it one more time. And let's kind of zoom this box so that we can kind of get a good idea of what's happening here. So we zoom box, my favorite zoom tool. First corner up here. Second corner right down here. Should give me a nice picture of this graph. There we go. I like it. Okay, so now we're going to graph our other one, negative x. So I'm going to go to tab. Tab, remember, is going to open me another window here. So I'm going to do negative x. Okay, so they're looking for the area enclosed between these two graphs. So we have this area right here and this area down here. So notice that the top function changes. So if you wanted to do this by hand, you would have to figure out what the intersection points are, right, which we're going to have to do anyway. And then you would have to integrate from this first intersection point to, it looks like 0, and then 0 to this intersection point using 2 separate integrals. It's actually possible to do by hand, so if you want to check the work that we get here with the calculator, not a bad idea. It's a good exercise to try this by hand. So you could find the intersection points just by going menu, where am I looking here? Analyze graph, intersection, left side, right side. We get one at negative 3, 3. And menu, intersection. Looks like we also have one at, drum roll, 4, negative 4. Okay, so we're integrating from negative 3 to 0 and then 0 to 4. And I actually have a picture of that from Desmos here. Okay, so our negative 3, 0, and 4 are where we have our intersection points. But there is a way to do this without having to break it into 2 integrals. And it's really nice because if these intersection points are really messy, remember the more times you use messy points, the less accurate your answer is going to be. So think about this. We know that we're supposed to integrate top minus bottom, right? Because we want this to be a positive number. If you do top minus bottom, it'll always give you a positive number. But if we have our calculator, what's a function we know that always makes things positive? You just do absolute value. So if you integrate from a to b, absolute f of x minus g of x, that will always give you the correct answer. Who cares how many intersection points there are? There could be a million. You could do like sine and cosine. This is a pretty common problem, actually. AP likes to ask this, and they have a bunch of these intersections. Instead of having to find every single intersection point, just integrate absolute value sine x minus cosine x. Who cares which one's on top? If it's positive, great. If it's negative, great. It's going to make it positive for the absolute. So this one I'm just going to integrate from negative 3 to 3. Sorry, to 4. Let's see here. So I'm going to do x cubed minus x squared minus 13x minus negative x, absolute value, dx. It's a great opportunity also if you have your functions defined. You can just integrate f of x minus g of x. In fact, that's what I think I'm going to do. So if I go to my home screen, I'm going to define, remember, do f parentheses x, colon equals is right next to the 9, colon equals, let's see, set that equal to x cubed minus x squared minus 13x. Okay, tells us it's done. Let's do g of x equals, control this guy, negative x. Okay, now I'm going to integrate. Menu, calculus, integral from -3 to 4. Absolute value is this guy next to the 9, right here, of f of x minus g of x dx. Super easy. Enter. There you go. 78.0833. There you go. That's all there is to it. All right. Wow. Okay, that was a lot. I think that's all I've got for you. So give the homework a shot. I love you guys. That's why I'm here. Have a great day.